Welcome to a deep dive into the statistical heart of machine learning model evaluation. Today, we're putting on our statistical lens to truly understand how well our models perform, focusing on the critical concepts of bias, variance, overfitting, and the powerful techniques of cross-validation and bootstrap resampling. Building effective models isn't just about training them, it's about rigorously evaluating their ability to generalize to unseen data, and statistics provides the bedrock for this crucial task. At the core of model evaluation lies the challenge of generalization. A model that performs flawlessly on its training data but falters on new, unseen information is ultimately useless. Our goal is to build models that learn meaningful patterns, not just memorize the noise in the training set. Statistical methods allow us to quantify and understand this generalization capability, ensuring our models are robust and reliable in real-world applications. Every model prediction carries an inherent error, and statistically, we can decompose this error into two primary components, bias and variance. Understanding these two adversaries is fundamental to diagnosing and improving our models. They represent different types of errors that prevent a model from accurately capturing the true relationship between features and target. Bias refers to the error introduced by approximating a real-world problem, which may be complex, by a simplified model. It's the consistent deviation between the model's predictions and the true values. A high-bias model makes strong assumptions about the data, leading it to consistently miss the relevant relations between features and target outputs. This often results in a scenario we call underfitting. On the other hand, variance is the error introduced by the model's sensitivity to small fluctuations in the training data. A high-variance model pays too much attention to the training data, capturing not only the underlying patterns but also the random noise within it. This oversensitivity leads to vastly different predictions when trained on different subsets of the data, a hallmark of overfitting. The bias-variance tradeoff is one of the most fundamental concepts in machine learning. It posits an inverse relationship. As we decrease bias, we often increase variance, and vice versa. Simple models typically have high bias and low variance, while complex models tend to have low bias but high variance. The art and science of model building lie in finding the optimal balance between these two, minimizing the total error. Statistically, detecting underfitting is often straightforward. An underfit model will exhibit high error rates not only on the validation or test set but also on the training set itself. When your model struggles to learn even the training data, producing low R-squared values for regression or poor accuracy for classification on both familiar and unfamiliar data, it's a strong indicator of high bias. The model is simply too simplistic to capture the underlying patterns. Conversely, statistical signs of overfitting are characterized by a significant disparity between training and testing performance. An overfit model will show excellent, often near perfect, performance on the training data, boasting very low error. However, when presented with unseen validation or test data, its performance drops considerably, revealing a much higher error rate. This large gap between training and test error is a clear red flag for high variance. To robustly assess a model's generalization ability, we turn to powerful statistical methods like cross-validation. Cross-validation is not just a technique, it's a paradigm for evaluating how well a model will generalize to an independent dataset. It systematically partitions the available data to ensure that every data point gets an opportunity to be in both the training and validation sets, providing a more reliable estimate of performance than a single train-test split. K-fold cross-validation is a widely used implementation of this principle. The dataset is divided into k equal-sized folds. The model is then trained k times. In each iteration, one fold is used as the validation set, and the remaining k1 folds are used for training. The final performance metric is the average of the k individual evaluation scores, providing a more stable and less biased estimate of the model's true generalization error. Another invaluable statistical technique for model evaluation is bootstrap resampling. Unlike cross-validation, which partitions the data, bootstrapping involves creating multiple resamples of the original dataset by sampling with replacement. Each resample is the same size as the original dataset, meaning some original data points may appear multiple times, while others may not appear at all. The applications of Bootstrap Resampling are diverse. It's particularly useful for estimating the variability of a model's performance metric, such as accuracy or R-squared. By training and evaluating the model on numerous Bootstrap samples, we can construct confidence intervals for our metrics, giving us a more nuanced understanding of the likely range of our model's performance in practice. It also helps in assessing the stability of model parameters. By integrating these statistical concepts and techniques, we adopt a holistic approach to model evaluation. Understanding the bias-variance tradeoff helps us diagnose problems, while cross-validation provides a robust estimate of generalization error. Bootstrap resampling then allows us to quantify the uncertainty around these estimates and assess model stability. Together, they form a comprehensive statistical toolkit for building reliable machine learning solutions. Ultimately, the statistical lens on model evaluation is not a one-time process but an iterative journey. It's about continuous diagnosis, refinement, and validation, ensuring that our machine learning models are not just intelligent on paper, but truly robust, generalizable, and trustworthy in the dynamic real world. The pursuit of minimal total error, balance between bias and variance, through rigorous statistical testing, remains our enduring mission.